We've talked a lot about LifeSim, the methodology that's going into it, the uncertainty. What you see here is LifeSim validation efforts. It's really not about validating the software, it's about validating the method and the thought processes that go into it. Okay, so I'll talk about our efforts to run against historic events. Talk about sometimes when we hit those historic events quite well, and sometimes when we didn't, and the reasons why, and go into a little more detail on the Joso case history. Model validation, just to get us all on the same page, right? It's how the process we use to model outputs and compare those to real world observations. And you just want to judge that quantitative correspondence with reality. So you think about our model, it's not just LifeSim. There's also the process we use to inform LifeSim, to come up with the inputs into our LifeSim approach. So that's a big piece of it. And ultimately, should we feel confident about what we're getting out of this? That's the whole point of why we're doing this. Do we have some level of confidence? Because we can sit around and talk about this theory that you've heard for the last 2 days and say we got it all in this great little computer model, but until you actually have some level of confidence that it's producing something meaningful, you should be very skeptical of all of this. So there's really 2 things that we're wanting to do here is demonstrate the validity with actual field data. So the first thing we're going to call this is model validation. We know what happened historically. We plug those into the modeling process and we get the results. So that's the model validation. The other part is what we call a process validation. If we didn't know what had happened, but we wanted to run through a scenario, say Hurricane Katrina coming in New Orleans, what would we have done following our typical processes to come up with a life loss estimate for that? And see if our typical processes get anywhere close to what actually happened, right? So our typical processes are going to have a lot more uncertainty about them, but if the actual results fall somewhere in the bounds of that, then we'll feel pretty good about it. So it's 2 slightly different things. What we're going to cover are these 4 different events, starting with New Orleans and then Joso. Real brief one on Kelly Barnes, which we heard the case history on, but how we modeled that. And some more on Malpasset, which we also have talked some about. So we're going to focus on the Orleans East Bowl. And one of the main reasons we picked this as one of our initial case histories was there was a really good documentation on what happened there. We had the IPET study, which was what the Corps did after Katrina to really do a forensic analysis of the flooding. And then we had something from Professor Jonkman out of the Netherlands who did his master's thesis on the fatalities. One part of his master's thesis was on the fatalities that occurred there. So we had a lot of good data to base this validation on. But this is just focused on the Orleans East Bowl for now. So what do we know? So back to the model validation. We know what happened. Let's force those inputs into the model and see if we get results that make sense or that are close to what actually happened. So we know in the East Bowl there's around 96,000 people, population at risk. Mandatory evacuation happened about 24 hours prior. And we know the evacuation rate was between 80 and 90%. We don't know exactly, but we know it was between 80 and 90%. We had a good inundation simulation from that IPET study. And we had a structure inventory that for the model validation, we were very careful about going through the historic imagery and making sure the structures were in the right place based on what happened prior to Katrina. And we also know there were 68 direct fatalities in this area. Here's that inundation simulation. It was, so this is something we'll talk a little bit more about. But it was not a full 2D model. It was done prior to 2D being built into RAS, so it was the storage area approach. For those of you that are H&H nerds, you'll know what that means. So start thinking about what that could do to the impact of your results and why it might matter. So the structures, like I said, we used some parcel data and verified that with aerial imagery, historic imagery, to get some really good confidence in the structures and a pretty good estimate of people being in those structures that we felt confident about. We forced the model to say, all right, after 24 hours, we're going to have 80 to 90% evacuation. So the whole point is set it up so we know only the 80, 90% of the people will be there when the water starts showing up. And here's the results. You still have a lot of uncertainty, but overall the results came out quite close. Obviously, we feel pretty good about that. But that's really only just looking at certain aspects of what LifeSim does in the overall process, right? And there's going to be a question. So I just want you to think about, by forcing all the inputs into LifeSim to do exactly what happened historically, what are you really validating in LifeSim by doing that process? And just start thinking about that. Okay, so the next thing is, that was forcing everything to do what we know what happened, the model validation. Now let's do the process validation. We didn't know what happened. We would use our standard approach like we would use on any study area and use our standard assumptions and see what kind of results we'd get. So population risk stayed the same. We evacuated 24 hours in advance. This is one of the standard MMC approaches for warning and evacuation, but there's a lot of wide bands. We had wide bands of uncertainty in terms of how people would respond. So instead of forcing it to that 80, 90%, we used our wide range of uncertainty that we've been talking about here. We're not sure what's going to happen. So we did that for both the warning and the PAI curve. We used the same inundation model. We didn't want to try to get into too many uncertainties, so we used the exact same inundation model. And instead of using that detailed parcel database, we used just the default download from the National Structure Inventory. Just pulled that in. We didn't make any modifications to it, just that real kind of quick and dirty, let's set something up. Again, the target 68 direct fatalities. And in this case, the results were quite a bit different. Quite a bit higher, still within the max and min, but that max and min is 3 orders of magnitude, so hopefully it still falls within. We've got a pretty big range there. So let's think about why that led to a bigger range and what some of those differences were, right? So we had the process validation and the model validation. So the maximum and the median is higher than the model validation through that process validation. Really, this is because of the difference in the structure inventory. If you just use the default settings and didn't move it to where the parcels were and using the aerial imagery, a lot of those structures were in low-lying areas that otherwise wouldn't have been there. So this reinforces that structure placement does matter, and it can matter a lot in these cases. So you got to be a little careful about just downloading data from some default database and saying, hey, I got a bunch of dots, that must be great, let's go. That's one of those ways you reduce uncertainty, is by doing a better job of structure placement. The minimum, so we also, from that process validation, the minimum was 6 instead of 27, and that can be explained by, we forced the model validation to evacuate between 80 and 90%. The process validation, we had a lot wider range of uncertainty, from 80% to 99% evacuation. So for those few times it sampled 99% evacuation, the resulting life loss is quite a bit smaller. So that's why you see a lot wider range, and that explains why some of those differences. So 2 questions here. Let's start with the one on the left. What component of the LifeSim, when we did that model validation, where we're really focusing on using all the inputs that we know, what are we really flexing? What are we really validating in the LifeSim model? The submergence criteria, how we differentiate people using that submergence criteria into high hazard and low hazard, and the fatality rates we apply to those in each one. If we had done a fully 2D approach, where you modeled the breaches and you did get some velocities, what would the result be of that? Really, the first answer is right. If you had some significant velocities and you start to see additional stability criteria for structures that may not have been submerged and get to the high hazard zone, but you're right next to a breach and that structure would have got washed away, then you would get slightly higher life loss. Like I said, in that area, it was mostly overtopping, not a lot of large breaches with high velocities, so it probably wouldn't have made a big difference is what the experts thought, but if anything, it would probably go up, unless the data was just a whole lot better. But it was a well-calibrated IPET model, so it was pretty good data. Next one, we're going to go into basically another case history and show how we did a validation of it. So this is, again, you've heard this name before, Paul Risher, now works for HDR. If you work for HDR, you should reach out to Paul Risher. He used to be an integral part of the LifeSim team outside of outside of the core. He's probably the most knowledgeable when it comes to application of LifeSim. You can tell him I was building him up. Tell HDR I was a good advertisement for him. So he put together this, and really he was working for us as kind of a long-term developmental assignment. He saw this flood occurring. He started following it on the news. He started capturing all this information. He started using Google Translate quite a bit and put all this together from his computer. And it's a really cool overall case history. So September 2015, like most floods, large hydrologic events came in and a whole bunch of rainfall occurred and caused riverine systems to fill up, including the Kinugawa River, which translates to River of the Demon's Wrath, which gives you an idea that things might be a little rough if you get a lot of water in there. So this is where we're talking about in Japan. There's a Joso levee breach. So this is kind of where we're located. Zooming in. So important part of this, and Stephanie just showed a simulation. We'll dive into this a little more. But started overtopping upstream first, and then a little bit later, the breach occurred right there where you can see it, the Joso breach. So I talked about this earlier today. Somebody had asked, hey, how's the warning go? And again, when they went back and looked at it in the case history, Paul pulled all this information out. The warning was kind of haphazard. In some cases, they got a flood advisory. Some cases, they got warned after the breach, some prior to the breach, and some didn't get a warning at all in this inundated area. So what this map shows is how relative to breach when that warning went out. Also put together a road network, which is really important for this one, so we'll talk more about that. So now I'm going to step through the timeline of what happened with some imagery to support that. 9:30, this is showing at 9:30 a.m., but the overflow started about 6 a.m. at that upstream location. Here's some images of people caught on roads around 11 o'clock, so they're no longer able to move. You can see people stuck there, so remember this, we'll talk about it more. This is on the levee crest, somebody driving by at 11:50, starting to see at the overtopping location where it ultimately ends up breaching, you start to see that erosion on the backside. This is shortly thereafter. Still, it's just the water from the overflowing the levee going through the neighborhood real close. This is a little bit later. That backside erosion has gone a lot farther. There was a road across the top that was preventing erosion of the crest, but now it's starting to get undercut, and then you'll see it breaches shortly thereafter. Now the same location, you got a lot more water coming through that neighborhood right next to the breach. This is based on some of the forensics that Paul did that talked about where people were, where structures were, and where they moved after the breach. Those two red dots are our best understanding of where the two fatalities were that happened during this flood event. Yellow are people were in the structures, and then purple is where people ended up out in the water and survived. Here's a drone footage at 5 p.m., so this is quite a bit later, but you can see the flood is still going on, the breach is wide open. And there's some other things looking in the background. What else do you see going on? Rescues. And there were a lot of those, and we're going to talk a lot more about that in a little bit. So, same thing, model validation, process validation. There was a survey done afterwards that Paul got his hands on that talked about how many people evacuated. He didn't have a lot of certainty or confidence in that survey. It wasn't as formal of a survey as we did after Oroville. It was much less informal, but that's all we had to go on, so that's what we're using here. But the hydraulics, we got a nice calibrated event that was modeled by Paul and other people at HEC. Structure inventory, we had somebody go through and do, they don't have national structure inventory over there, so somebody went through and put every structure out there using aerial imagery and Google Street View. And then the hazard identification, similar to what we did for Katrina, for the model validation, we forced it to do what the survey said occurred. And then for the process, we used our just standard process of what we normally would have modeled. So here's the inundation, simulation of the inundation. It starts overtopping upstream, then the breach occurs further downstream, and then the rest of the leveed area starts to fill up. Here's that protective action initiation. For those that, so we know overall it was between 40 to 60, or around, 60% of the people evacuated, 40% didn't. And what we did is, for those that received the warning, we had them get there a little bit quicker than those areas that didn't receive the warning. But overall, we didn't have enough information to differentiate between the different areas in terms of how many people ultimately evacuated. This is what that looks like. So this hopefully helps explain what you saw earlier when Stephanie showed it, was why certain people are evacuating in certain areas, and then it spreads because that's when the warnings went out. So this was our model validation results. We went through, set it all up with what we thought was the best available information, and got something quite a bit different than when you saw the last one, right? So not even in our range of from max to minimum. So the next step is now we got to figure out why. What are we missing in our approach to modeling this to help us explain either we're doing something completely wrong or there's just something missed here. And that's where this concept and thought process of the rescue starts to come in. This is 11 a.m. We showed that a little bit earlier. This is shortly thereafter. That car's underwater, and there's a boat there that has the people off of the car in the boat, right? So what would have happened to those people? They would have probably had a rougher time. There's no guarantee that they would have lost their life, but they would have been in a tough situation. So there were reports of many rescues like this that we think had a pretty significant influence on ultimately on how many people lost their life. What you're seeing here is this house and where it moved. It started over there on the right. You can see it here moving, and then it comes to rest against that structure. The brick structure, higher stability criteria, over there on the left. We're going to see a video of that. But if that other house hadn't been there to stop it, who knows what the result's going to be. We're going to talk about the story of the Sakai family. Retired couple and an adult son living at home 200 feet from the breach is where their house was. Around noon, so I don't know if you remember that timeline, but around noon, the father said, wait, this is weird. Where's all this water coming from? I'm going to go look at the breach. The wife and son stayed home. So another thing that I like to have people think through is like, you hear a lot of time, you go out and say, well, they're going to see the water coming over the levee, they're all just going to leave. And that's not how humans always react, right? He's like, well, you guys go upstairs, I'm going to go check out what's going on. So he walked out there. Nobody told him to evacuate, but he saw what was going on. So here's a video of the people that stayed at home. Down there, the grandma went under earlier, hasn't popped back up yet. That's the son that you still see in the camera there. He ends up floating just a little bit further downstream. The mom popped up over there. He floats just a little bit further downstream, and you'll see it stands up and walks off, right? So it's that far. But she stayed there, hanging on, grasping onto whatever she could, probably getting tired. There's that whole duration component of how long can you last in something like that. And the rescue showed up shortly thereafter and pulled her out of there, right? So you think about that, how much did rescues like that end up influencing the overall life loss from an event? So Paul did some digging into it. There were a lot of rescues like that. Like I said, we think it's a significant amount. Whether that makes up the whole difference between what we modeled versus what actually occurred, probably not, but it makes a difference. And so that's something important. LifeSim doesn't talk about rescues, right? There's no helicopters flying around simulating people, pulling them out of difficult situations. Yet. Next week.
Are you saying the observed number was 2 and I forget what the model was?
We were up around 30, yeah. So, like I said, it probably doesn't make up for all of it. I think another big part of this uncertainty is we were relying on the percentage of people that evacuated. It's a pretty low number based on that survey that we weren't that confident in. So maybe in reality more people evacuated. So that's some other stuff to think about.
There wasn't anything in your models that would change necessarily beyond those results for the model?
If I was doing it, I would probably add some more uncertainty to the mobilization, to how many people chose to evacuate, just to see how big of an influence that had. But no, specific to this, we'll talk about that in just a second, what I would do. Okay, so what did we learn about this? Oh yeah, so the dad, he didn't make it out to the levee. He got washed down a little bit. He ended up hanging onto a telephone pole until he was rescued as well. The son, we saw, got washed out and then walked away. Poor information, they weren't warned and told to evacuate. Questionable decision making because they saw what was going on and didn't evacuate. That's the model validation, not great. Let's follow through with our standard processes. So we wouldn't break it down into a bunch of little warning areas based on what actually happened. We'd say, all right, it's all one county, all one EPZ, let's treat it all the same. And use our wide range of uncertainty on how quickly warning spreads and how many people respond, just like we did for Katrina. And now our range is lower, and it encompasses what actually happened. And a lot of that can be explained by, again, you have a much more optimistic outcomes in terms of how many people ultimately tried to evacuate. So when it samples a lot of people got warned and mobilized, they could get out of the way, is what this is showing. And this is the same thing, but you'll see something slightly different because everybody gets warned at the same time, everybody starts moving. Right? A couple slides on Kelly Barnes. I'm not going to go into a lot of detail on this one. You've heard the case history from Jesse, but we ran this through the similar process. So there's a great book if you want to hear the details of what happened. The dam break in Georgia, Sadness and Joy at Toccoa Falls. So again, being able to do these validation studies requires a lot of good data to base that on, right? You have to have an idea of how many people were there. You have to have an idea of kind of the warning, how many people got out of the way, where the life loss occurred to be able to do some validation like this. It's not easy. You don't have those for all the historic studies. We also got a good 2D RAS model from the group at HEC. So it looked a lot like this. You've heard about Trailerville. You can kind of see it. Which structures survived, which ones didn't. We had a good accounting of how many people were in each one of those and which ones died and which ones didn't. So that was some really good data. So we ran that through similar to what you saw previously. So population was around 150, no formal warning, just environmental cues. So we set our warning time for 15 minutes after breach, because that's when people started to understand there was a problem and the warning was spreading. Road network based on that historic imagery, that calibrated 2D model, and the structures based on the building footprint. 39 direct fatalities. And in summary, I'm not going to go into all the details. This one came out pretty good as well in terms of the historic account versus our range. So again, that one helped us feel good about a lot of what's going on in our method. Last one, Malpasset Dam Failure, 1959, southeastern France, along the Mediterranean coast, right upstream of the town of Fréjus. Another disaster, nighttime, 1959. A lot of rain, filled up the reservoir, and there was a concrete dam that collapsed, sudden collapse. So that's not good, something a little bit different than we've seen. Small village in the canyons were destroyed, the larger town of Fréjus suffered a lot of damage. Less than 30 minutes, the thing was over, washed all the way out to the sea. So for this one, what we know for our model validation is population at risk, no formal warning. So a lot of what we know from this was based on research done by a group from BC Hydro, where they went in, so BC Hydro has another model called the life safety model that is similar to what LifeSim does at trying to model the agent-based model. It has some strengths, but it hasn't had nearly as many resources invested in it to really make use of a lot of the more recent technology and all the development that we've been able to do. So it's similar, but they're doing the same thing. They're trying to go out there and say, hey, can we model something like this and get similar results to what actually happened? So that's where we got all this data. So there's a calibrated Telemac 2D. So this one's slightly different because now we're going to show a little bit of uncertainty in hydraulic results. You do a Telemac 2D model and an HEC RAS 2D model that both try to hit that calibrate to the actual event as close as possible. Are you going to get significantly different results in life loss just because of that? We had population in each zone, building locations, and this one was 423 direct fatalities. And you can see how that's broken down. So up here, the dam is right up here at the top of this gray area. And then you have the upper and lower Rayron valleys, the town of Fréjus, and then the surrounding area. And this is the life loss observed in each one of those areas. So here's the results. And I'll break this down. So over here on the left is using the Telemac 2D hydraulic data plugged into LifeSim. The purple is the HEC RAS 2D plugged into LifeSim. And the green, the Telemac, and the purple both use the same stability criteria. So we've talked about stability criteria and what we did for this and how it mattered for this event. So those are both with wood framed, but thinking about it a little bit more, like back then, a lot of what they had was more of the masonry type buildings in that area. So this whole study, when we came out with this at the beginning, we're like, wait a second, we got to do better on stability criteria here. And I pretty sure this is what led Stephanie to become an expert on stability criteria, because she was out doing developmental with us, and we said, here's a whole bunch of data, consolidate, make sense of it, and help us get the stability criteria with a good understanding of and supporting evidence for what we're using. So after we got through that, came up with good stability criteria for masonry, plugged that in, and got the results that you see over there on the right. So using the RAS 2D model with stability criteria that we thought was representative of the buildings that were out there, we got results that were pretty close to what happened in reality. But again, this is a good way to show some of the uncertainty and the range of impacts when it comes to stability criteria and difference in hydraulics. There can be a pretty significant difference, even just between two different hydraulic models that are giving you similar results. So here's a summary of what actually happened versus the different approaches. And again, this one again was mostly about stability criteria and fatality rates, right? You're not flexing many muscles of the warning, dissemination, and the evacuation process, because there was no warning, there's no evacuation. You just put a bunch of water on people and structures and see what the life loss could be. Hey, I appreciate you all hanging in. I know that some of these can be long days. It's a lot of information being thrown at you, so I appreciate your attentiveness and helping us get through this. So.